May 34, 1916 unfolded as a day of profound consequence in the North Sea, specifically off the Danish coastline. Rear Admiral Hugh Evan Thomas stood steadfast on the bridge of HMS Barham, his gaze fixed upon the ominous spectacle of the German high seas fleet emerging from the dense mist, appearing like ethereal gray specters. His command consisted of 4 majestic Queen Elizabeth-class battleships, which at the time represented the zenith of British naval engineering. These formidable vessels were formidable, equipped with 15-inch gun barrels capable of propelling 1-ton shells across an astonishing distance of 15 miles, embodying the pinnacle of destructive power. Yet, a critical and potentially devastating flaw was rapidly manifesting, poised to exact a terrible toll in British lives. 6 miles ahead, Vice Admiral David Beatty's squadron of battlecruisers was already engaged, hurtling towards the German battle line at a blistering 25 knots. Beatty, recognizing the dire need for reinforcement, urgently signaled Evan Thomas to follow at the utmost speed his ships could muster. However, Evan Thomas's battleships, despite their magnificent stature and immense firepower, were inherently limited to a maximum speed of 24 knots, a pace that already pushed their reciprocating engines to their absolute operational limit. The mathematical reality of the situation was stark and unforgiving. With each passing minute that Evan Thomas's squadron lagged, the distance between the 2 British forces inexorably expanded by 100 yards. This widening chasm left Beatty's swifter, though more lightly armored ships to confront the formidable German dreadnoughts alone, a perilous imbalance that quickly led to catastrophic losses. At precisely 4:00 p.m., the HMS Indefatigable was engulfed in a cataclysmic explosion, a direct consequence of a German shell detonating her magazine. In a horrifying instant, 1,017 men perished. Just 26 minutes later, at 4:26 p.m., the HMS Queen Mary met a similar fate, disintegrating in a massive fireball, claiming another 1,266 lives. Beatty, a first-hand witness to the horrific spectacle of his fleet ablaze, uttered words that would forever resonate through the annals of naval history. There seems to be something wrong with our bloody ships today. However, the fundamental issue was not an inherent defect in the ships themselves. Rather, the core problem lay with their propulsion systems, specifically the choice Britain had made a decade earlier. This decision, widely condemned by every admiral as suicidal and by every naval engineer as a guaranteed path to fleet destruction, defied conventional wisdom and was declared impossible by many. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. In 1906, one audacious individual staked Britain's long-held naval supremacy on a radically novel propulsion system, despite dire warnings from senior officers that it would literally tear ships apart at sea. This visionary was Charles Algernon Parsons, remarkably not a naval officer himself, but a civilian engineer whose professional life had been dedicated to the construction of electrical generators. Unbeknownst to Evan Thomas, as he stood on Barham's bridge, watching his ships valiantly but futilely struggle to close the gap with the enemy, his battleships were already technologically superseded. They were still propelled by the very same reciprocating steam engines that had served warships for half a century, systems characterized by massive pistons, relentlessly hammering up and down, converting steam pressure into mechanical motion through sheer brute force. Meanwhile, a mere 6 miles ahead, HMS Lion, Beatty's flagship, was driven by an engine of truly revolutionary design. This innovation was something that virtually every expert had confidently declared unworkable. Yet it was precisely this technology that enabled British battlecruisers to operate at speeds utterly unattainable by vessels reliant on reciprocating engines. While the Battle of Jutland ultimately concluded in a tactical draw, it unequivocally demonstrated, through the crucible of blood and fire, that Charles Parsons' purportedly suicidal invention had permanently altered the landscape of naval warfare. The era dominated by the reciprocating engine had definitively ended, and the age of the turbine had dawned, all initiated by one man's unwavering refusal to accept what everyone else considered an insurmountable impossibility. The genesis of this profound technological dilemma can be traced back to 1890, when Britain confronted a formidable strategic quandary. The Royal Navy, with its impressive fleet of 38 battleships, reigned supreme over the world's oceans, outnumbering any other nation's naval power. However, a troubling trend had emerged. Battleships were becoming progressively slower rather than faster. The primary culprit was the reciprocating steam engine, a technology fundamentally unchanged from the basic design that had propelled Britain's inaugural steam warships 6 decades prior. In essence, steam generated from boilers drove pistons in an oscillating up-and-down motion. These pistons, in turn, rotated a crankshaft, which then spun the ship's propellers. While functional, this system harbored severe inherent limitations. The swiftest pre-dreadnought battleships struggled to surpass a modest 18 knots. Admiral Sir John "Jackie" Fisher, widely recognized as Britain's most aggressive and forward-thinking naval reformer, meticulously calculated that in any large-scale fleet engagement, the slower force would inevitably face systematic annihilation. His conclusion was unequivocal. Speed was synonymous with survival, and speed was the ultimate determinant of victory. However, reciprocating engines had undeniably reached their physical and practical limits. Engineers tirelessly explored every conceivable avenue for improvement. They constructed larger engines, only to discover that the increased weight paradoxically slowed the ship down. They boosted boiler pressure, but this led to a corresponding surge in mechanical failures. They incorporated more cylinders, only to find that such complexity bred unreliability. By the turn of the century, around 1900, a consensus had firmly solidified. 18 knots represented the absolute maximum speed a battleship could ever hope to attain, with the prevailing belief that the immutable laws of physics would simply not permit anything faster. Then came the inevitable acceleration of the global arms race. In 1898, Germany embarked on an ambitious program to construct a modern battle fleet explicitly designed to challenge British naval hegemony. Kaiser Wilhelm II famously declared, "Our future lies on the water," signaling Germany's intent to become a dominant maritime power. Germany's newly commissioned battleships were meticulously engineered to match British speeds, knot for knot. This development effectively rendered Britain's long-standing numerical advantage meaningless if German vessels possessed equivalent speed capabilities. Admiral Fisher, a man of profound conviction and relentless drive, assumed the prestigious position of First Sea Lord in 1904. At 63 years old, he was known for his fiery temperament and brilliant strategic mind. But he was also acutely terrified that Britain was on the precipice of relinquishing its naval dominance. In response, he convened a highly secretive body, the Committee on Designs, with the explicit mandate to conceptualize and develop a revolutionary new battleship. Oh, the specifications laid out for this new class of warship were utterly unprecedented. It was to be armed with 10 12-inch guns, effectively doubling the main armament of existing battleships, feature exceptionally heavy armor, and, most critically, possess a top speed of at least 21 knots, a full 3 knots faster than any battleship currently in service anywhere in the world. The established engine manufacturers unequivocally informed Fisher that achieving such a speed was an impossibility with conventional reciprocating engines. They projected that it would necessitate doubling the engine size, which would in turn add an additional 2,000 tons of weight to the vessel. Such a ship, they argued, would be excessively large, prohibitively expensive, and would likely shake itself apart due to the immense vibrations generated by massive pistons hammering at such high speeds. Fisher's own engineers presented him with a series of grim and sobering calculations. A reciprocating engine operating at its absolute maximum speed would generate catastrophic levels of vibration. One could vividly imagine a 500-ton piston assembly violently hammering up and down an astonishing 75 times every minute. While at 18 knots, these vibrations were deemed manageable. Pushing the speed to 21 knots meant that the oscillations could potentially crack the ship's keel, shatter crucial bearing surfaces, and precipitate mechanical failures that would inevitably leave the warship dead in the water. The Admiralty's chief engineer, Sir Henry Oram, articulated the problem with blunt clarity. "We've reached the limits of what reciprocating machinery can do. If you want 21 knots, you need fundamentally different technology." But the critical question remained: what alternative technology could possibly fulfill these demanding requirements? Every warship across the globe, without exception, relied on reciprocating engines. They were tried and tested, demonstrably reliable, and naval officers thoroughly understood their operation. Furthermore, shore facilities were fully equipped and staffed to repair them. To switch to an experimental technology would be to gamble Britain's naval supremacy, the very bedrock of its vast empire, on unproven machinery. The strategic stakes could not have been higher. Britain, dependent on imports for 60% of its food supply, relied entirely on the Royal Navy to safeguard these vital supply lines. To lose naval supremacy was to invite national starvation. Admiral Fisher was acutely aware that the German battle fleet was expanding at an alarming rate of 12 new capital ships per year. Britain urgently needed a technological breakthrough, and it needed it immediately. The critical demand for a new, powerful naval propulsion system was immediate and pressing. In November of 1904, a specialized committee, led by the astute Admiral Fisher, meticulously scrutinized a considerable array of 43 distinct proposals for ship propulsion. The vast majority of these submissions were merely incremental modifications of the existing, well-established reciprocating engine designs. Universally, these conventional concepts proved incapable of satisfying the stringent requirement for a top speed of 21 knots without incurring unacceptably severe penalties in terms of overall vessel weight. Amidst this technical impasse, a name emerged from the discussions: Charles Parsons. Intriguingly, Parsons was not a seasoned naval engineer. He had never before conceived or crafted a warship. His professional domain lay in the construction of electrical generators and various types of industrial machinery. However, he had been diligently pursuing experimental work with an innovative technology he termed a steam turbine, which represented a profoundly novel methodology for converting the raw energy of steam into continuous rotational motion. In stark contrast to the percussive back-and-forth action of hammering pistons, Parsons' ingenious design harnessed the smooth, directed flow of steam through an intricate arrangement of precisely angled blades, thereby causing a central shaft to spin fluidly and rapidly, achieving thousands of revolutions per minute. The initial reaction from the established naval officers was one of immediate and unequivocal dismissal. They viewed the nascent turbine technology with deep skepticism, branding it as unproven, inherently complicated, and fraught with unacceptable risks. Yet Admiral Fisher, facing an increasingly dire strategic situation, found himself in a state of profound desperation, recognizing the urgent need for a radical breakthrough. It was in this crucible of necessity that Charles Parsons, the perceived amateur and outsider, was poised to demonstrate a profound truth: that occasionally an unconventional mind can discern groundbreaking solutions that elude even the most seasoned and specialized experts. Charles Algernon Parsons, by 1904, had reached the age of 50. Although born the son of an Irish earl, a title that typically implied a life within aristocratic drawing rooms, he had instead chosen a path deeply immersed in the practical realities of engineering workshops. His intellectual foundations were forged at Cambridge, where he pursued a rigorous education in mathematics. Throughout his career, he had lent his considerable talents to various industrial enterprises, focusing on the design of dynamos and sophisticated electrical apparatus. His hands bore the unmistakable marks of extensive manual labor, a testament to his practical engagement. And his intellect was ceaselessly occupied with the intricate mechanics of motion and the subtle efficiencies of thermodynamics. Despite this formidable technical prowess, he possessed absolutely no prior experience in the specialized field of naval architecture or marine engineering. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. It was 2 decades earlier, in 1884, long before Fisher's committee ever contemplated reaching out to him, that Parsons had successfully constructed his very first operational steam turbine. The fundamental principle underpinning his invention was remarkably elegant in its simplicity. Rather than employing the expansive force of steam pressure to drive pistons in a linear, reciprocating fashion, his design ingeniously channeled the high-velocity steam through a series of meticulously crafted blades affixed to a rotating shaft. The kinetic energy inherent in the flowing steam imparted a tremendous rotational impetus to these blades, causing the shaft to spin at extraordinarily high velocities, reaching up to an astonishing 18,000 revolutions per minute. The beauty of this system lay in its complete absence of reciprocating motion, eliminating the jarring percussive vibrations typically associated with piston engines, and instead delivering a seamlessly smooth, continuous rotation. Predictably, the entrenched engineering establishment met his radical innovation with widespread derision and open laughter. the esteemed institution of mechanical engineers, a bastion of conventional thought, outright rejected his initial scholarly papers, detailing the turbine's principles and potential. One particularly dismissive reviewer encapsulated the prevailing sentiment, writing with condescending certainty that Mr. Parsons' turbine is an interesting toy, but it will never replace the reliability and power of reciprocating engines for serious applications. Undeterred by this professional scorn, Parsons resolutely ignored his critics. Instead, he channeled his energy into founding his own enterprise, C.A. Parsons and Company, strategically concentrating his efforts on the burgeoning field of electrical generation. His innovative turbines proved to be exceptionally well suited for the task of spinning generators at constant high speeds, a critical requirement for efficient power production. By the turn of the century 1900, his company had achieved considerable commercial success, having installed numerous turbines in power stations spread across Great Britain, establishing a profitable and thriving business. Yet, Parsons harbored an even grander ambition, a profound conviction that his turbines possessed the inherent potential to utterly revolutionize marine propulsion. The formidable challenge, however, lay in persuading anyone within the conservative maritime industry to actually embrace and implement his pioneering technology. In a bold move to provide tangible proof of his concept, Parsons commissioned the construction of a 100-foot yacht in 1894, which he christened Turbinia. From an external perspective, the vessel appeared largely unremarkable, blending seamlessly with other pleasure craft of its era. However, beneath her unassuming deck lay a truly revolutionary power plant, a Parsons steam turbine, capable of generating an impressive 2,000 horsepower, which drove 3 propeller shafts at speeds that conventional reciprocating engines of the time could simply never hope to attain. On the auspicious date of June 26, 1897, Parsons executed a truly audacious maneuver that would etch his name into naval history. This was the occasion of Queen Victoria's Diamond Jubilee Naval Review, an unparalleled spectacle unfolding at Spithead, featuring a magnificent parade of 165 warships, each representing the formidable might and global reach of the British Empire. The event was strictly by invitation only, and Parsons, conspicuously lacking such an official summons, decided to brazenly crash the prestigious gathering. Suddenly, Turbinia materialized amidst the vast array of anchored warships, her powerful turbine emitting a distinctive, high-pitched scream and spray arcing dramatically from her bow. She swiftly accelerated to an astonishing 34 knots, a speed that rendered her the fastest vessel in the entire world. The Royal Navy, stunned by this unexpected intrusion, dispatched its fastest patrol boats with orders to intercept the rogue yacht. However, these naval craft could only manage a maximum speed of 27 knots. Turbinia effortlessly outran them, weaving with almost contemptuous ease between the colossal battleships, effectively making the proud Royal Navy appear utterly foolish in the presence of their sovereign. Understandably, the ranking naval officers were absolutely furious at this blatant breach of protocol and public embarrassment. The Admiralty, the governing body of the Royal Navy, even contemplated legal action, considering prosecuting Parsons for unauthorized intrusion into a restricted naval event. Nevertheless, amidst the official outrage, a contingent of younger, more forward-thinking officers found themselves genuinely intrigued by the turbine's undeniable performance. This nascent interest led to further experimentation. In 1899, the destroyer HMS Viper was fitted with experimental turbines and remarkably achieved a speed of 36 knots, a velocity that had previously seemed utterly impossible for a warship. Tragically, Viper subsequently ran aground and was lost in 1901. Another destroyer, HMS Cobra, also received turbines, but she catastrophically broke apart in heavy seas in 1901, claiming the lives of 67 men. These unfortunate failures served to reinforce the prevailing conventional wisdom within the Navy. Turbines were perceived as excessively risky, too experimental, and far too dangerous for deployment in crucial capital ships. Yet, in November 1904, as Fisher's committee grappled desperately with the intractable problem of achieving higher speeds, the extraordinary memory of Turbinia's spectacular performance resurfaced vividly in someone's mind. The committee members vividly recalled that audacious experimental yacht effortlessly dancing through the review fleet at speeds previously deemed impossible. Promptly, Admiral Fisher issued a summons for Parsons to appear before the Admiralty. Parsons arrived, well prepared, armed with meticulously detailed drawings, complex calculations, and a decade's worth of comprehensive test data, gleaned from the continuous operation of his turbines in both power stations and various merchant vessels. He presented Admiral Fisher with a compelling proposal to install his advanced steam turbines in the new revolutionary Battleship. Parsons argued persuasively that his turbines would be significantly lighter than their reciprocating engine counterparts, would generate substantially less vibration, demand fewer crew members for operation, and most critically, they would reliably deliver the coveted 21-knot speed required. Fisher's senior officers, however, reacted with profound horror to this radical proposition. "It's suicide," declared the outspoken Admiral Reginald Custance, expressing the collective apprehension. He elaborated on their fears, stating, "We'll be putting the most powerful warship ever built at the mercy of unproven machinery. If the turbines fail in battle, the ship is helpless." The weight of tradition and the fear of the unknown hung heavy in the air. Yet Parsons possessed one final, powerful argument that effectively silenced the chorus of objections. He made an unprecedented offer. He personally guaranteed the performance of the turbines. If they failed to meet the specified requirements, he pledged to replace them entirely at his own considerable expense. This was a monumental wager, a bet worth hundreds of thousands of pounds, effectively everything he owned and had painstakingly built. Admiral Fisher gazed intently at the civilian engineer, a man willing to risk financial ruin on the absolute faith he held in his own invention. Then Fisher's thoughts turned to the tangible and growing threat posed by the German fleet across the North Sea, a looming challenge that demanded a decisive advantage. With a resolute expression, Fisher issued his momentous order: "Build it." Parsons promptly returned to his bustling factory in Newcastle upon Tyne, invigorated but also burdened by the immense task ahead. He was allotted a mere 16 months to meticulously design, construct, and rigorously test the colossal turbines destined for the new battleship, a vessel that would soon be known as AHMS Dreadnought. The deadline was, by any measure, absolutely insane, demanding an unprecedented pace of innovation and production. The stakes involved were nothing less than Britain's enduring naval supremacy on the global stage. The pressure bearing down on Parsons and his team was, quite simply, crushing. The engineering challenges confronting Parsons were truly immense and multifaceted. A typical power station turbine, for instance, operated at a constant speed, humming peacefully and reliably for months on end. In stark contrast, a battleship turbine would be subjected to far more brutal and dynamic conditions. It would be required to accelerate from a complete standstill to full power within a matter of minutes, handle rapid and frequent changes in speed, reverse its direction of rotation instantly, and, crucially, possess the structural integrity to survive the devastating impacts of battle damage. Parsons had never before attempted to construct anything remotely approaching the sheer scale and operational complexity demanded by this naval application. He meticulously calculated the immense power requirements. A staggering 23,000 shaft horsepower would be necessary to propel an 18,000-ton battleship through the water at the target speed of 21 knots. This formidable power output necessitated the installation of 4 massive turbines, configured as high-pressure and low-pressure pairs, to drive the port and starboard propeller shafts independently. Each individual turbine would need to maintain a rotational speed of 380 revolutions per minute, while simultaneously managing superheated steam pressurized to an extreme 265 pounds per square inch. Operating under immense pressure, specifically 265 pounds per square inch, the meticulous design of the turbine blades proved absolutely paramount. Parsons, the visionary engineer, embarked on an exhaustive series of experiments, meticulously evaluating hundreds of distinct configurations. His trials encompassed a vast spectrum of parameters, scrutinizing various angles, exploring different materials, and adjusting diverse spacings. He discovered a delicate equilibrium. If the blades were pitched too steeply, the vital flow of steam would be significantly impeded, compromising efficiency. Conversely, a pitch that was too shallow would prevent the blades from adequately extracting the necessary kinetic energy. The precision demanded in this endeavor was astonishing, with manufacturing tolerances measured in mere thousandths of an inch, reflecting the critical nature of every minute detail. In the pivotal month of April 1905, Parsons initiated the momentous test firing of the inaugural turbine within the confines of his own workshop. The sheer scale of the rotor assembly was formidable, a colossal steel drum weighing 50 tons, meticulously engineered and adorned with countless precisely milled blades. He commenced the process by gradually increasing its rotational velocity, his gaze intently fixed on any nascent vibrations. At a modest 100 revolutions per minute, RPM, the entire apparatus appeared remarkably stable. However, as the speed climbed to 200 RPM, the very structure of the building began to perceptibly vibrate. By the time it reached 300 RPM, a palpable sense of terror was etched upon the faces of his attending engineers. Undeterred, Parsons resolutely pushed the machine to its full operational speed of 380 RPM. The resulting cacophony was utterly deafening, a roaring testament to the immense power unleashed. The turbine housing itself glowed a vivid red, a testament to the intense heat generated by the high-pressure steam. Yet, remarkably, the vibration remained minimal, an astonishing feat that far surpassed the inherent instability of any reciprocating engine. Parsons vigilantly monitored a suite of critical parameters, including bearing temperatures, the intricate flow of steam, and the overall power output, confirming that every metric remained well within specified limits. He subjected the turbine to rigorous endurance tests, operating it continuously for 6 hours, then extending the trial to 12, and ultimately to a full 24 hours. Through these exhaustive trials, he conclusively demonstrated a level of unwavering reliability that no contemporary reciprocating engine could ever hope to rival. However, amidst this triumph, a significant and unforeseen challenge emerged: the imperative of reversing the powerful machinery. Battleships, by their very nature, necessitated the capability to execute high-speed reversals for a multitude of crucial operational requirements. These included precise docking maneuvers, intricate tactical repositioning during engagements, and swift emergency stops to avert peril. Traditional reciprocating engines offered a straightforward solution, reversing their direction simply by altering the motion of their pistons. Turbines, however, were inherently designed to spin in a singular, unidirectional fashion. The fundamental question then arose: how could such a formidable, single-direction engine be effectively reversed? Parsons' ingenious, albeit radical solution involved the installation of entirely separate turbines specifically dedicated to reverse operation. This innovative approach meant that each vessel would be equipped with a grand total of 8 turbines, 4 designated for forward propulsion and an additional 4 dedicated solely to reversing maneuvers. While undeniably brilliant, this system introduced significant layers of complexity and considerable expense, precisely the kind of intricate and costly complication that invariably generated profound apprehension and unease among the conservative ranks of naval officers. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment below about where you are from and what you think about the video topic. In August of 1905, a pivotal moment arrived when Admiral Sir William May paid a formal visit to Parsons' bustling factory, his purpose being a thorough inspection of the revolutionary turbines. He observed with keen interest the colossal rotors as they spun, their motion generating a smooth, almost imperceptible hum. He also noted the remarkably minimal vibration, a stark contrast to the clatter of traditional engines. After absorbing these impressive demonstrations, he posed the question that had, until then, remained unspoken, a latent fear shared by many. What catastrophic consequences would ensue if a single blade were to fracture at full operational speed? Parsons, with stark honesty, elucidated the dire scenario. A broken blade, he explained, would inevitably trigger a severe imbalance within the spinning assembly. This imbalance would, in turn, cause the turbine to vibrate with escalating and violent intensity. In the most extreme and catastrophic event, the entire unit could literally tear itself apart, unleashing a lethal barrage of shrapnel that could easily penetrate the ship's hull, with the terrifying potential to send the entire vessel to the bottom of the sea. That grim prognosis aligns precisely with my own fears, Admiral May responded, his voice grave. You are, in essence, demanding that we place our absolute trust in these blades, components that will become utterly invisible once installed, incapable of any inspection during their operational lifespan, and spinning at hundreds of revolutions per minute, with the unwavering conviction that they will never, under any circumstances, fail. Yes, Parsons affirmed simply, his gaze unwavering. That is precisely the audacious trust I am requesting. May fixed Parsons with a long, incredulous stare before declaring, That, Mr. Parsons, is nothing short of insanity. No, Admiral, Parsons countered quietly, his voice imbued with a profound conviction. What is truly insane is to forfeit our preeminent position in the escalating naval arms race, simply because we are paralyzed by a fear of embracing essential innovation. Following this tense exchange, the turbines were duly dispatched to Portsmouth Dockyard in October 1905, where the mighty hull of HMS Dreadnought stood in readiness, awaiting its revolutionary heart. By December 2, 1905, the Portsmouth Royal Dockyard hummed with activity. HMS Dreadnought, the embodiment of a new era in naval warfare, lay majestically in dry dock, her construction approximately 90% complete. Her sheer size was awe-inspiring, stretching an imposing 526 feet in length, her decks bristling with an unprecedented array of 10 powerful 12-inch guns housed within 5 revolutionary turrets. She presented a silhouette unlike anything the naval world had ever witnessed, a stark departure from conventional design. And it was this groundbreaking vessel that was poised to receive the most controversial and technologically advanced machinery ever contemplated for installation in a warship. The highly anticipated installation of the turbines was officially slated for December 5th. However, on December 3rd, a formidable delegation of senior naval officers unexpectedly arrived at Portsmouth, spearheaded by the influential Admiral Lord Charles Beresford. Beresford was a well-known and bitter rival of Admiral Fisher, a staunch traditionalist who vehemently believed that the entire turbine experiment constituted a reckless and irresponsible gamble with the precious lives of British sailors. Beresford, wasting no time, immediately demanded an emergency meeting with the dockyard superintendent. Parsons was swiftly summoned to attend. The tense and pivotal meeting ultimately convened in the Admiral's imposing office, which offered a commanding view of the bustling harbor below. "Mr.
Parsons," Beresford commenced, his voice laced with unmistakable condescension, "I have meticulously scrutinized your turbine specifications. Furthermore, I have consulted extensively with a multitude of experienced marine engineers. Their collective consensus is unequivocally clear. Your machinery is fundamentally unsuitable for deployment in a capital ship of such strategic importance." Parsons, maintaining an admirable composure, kept his voice steady as he inquired, "May I respectfully ask what specific technical objections have been formally raised?" Beresford, with a theatrical flourish, pulled out a meticulously prepared list. "Where, indeed, shall I even begin?" he retorted. "Firstly, your turbines are inherently incapable of rapid reversal. In the heat of a fleet engagement, precious seconds can mean the difference between victory and defeat. Your overly complex reversing system will inevitably compromise our tactical flexibility on the high seas." Parsons, ever ready, calmly countered, "Our comprehensive measurements have unequivocally demonstrated that the dedicated reversing turbines actually respond with greater alacrity than traditional reciprocating engines." "Secondly," Beresford interjected, cutting off Parsons' explanation, "your turbines exhibit a marked inefficiency at lower speeds. A battleship, by its very nature, spends the vast majority of its operational life cruising, not engaged in high-speed sprints. Your current design, therefore, will undoubtedly consume an excessive and unsustainable quantity of fuel." "We have meticulously addressed that particular concern," Parsons responded, "through the innovative incorporation of a specialized low-pressure turbine stage." Thirdly, and most damningly, Beresford's voice escalated, imbued with a sense of finality, "your turbines represent a catastrophic single point of failure. Should even one turbine malfunction,
the entire ship would lose propulsion on that specific shaft. In stark contrast with reciprocating engines, we possess the capability to effect repairs even while at sea. Your turbines, however, are sealed, monolithic units. If they fail, the ship is rendered effectively helpless, forced to limp ignominiously back to port. A profound and heavy silence descended upon the room. The devastating weight of Beresford's argument was palpable, its logic resonating deeply with everyone present. Parsons himself recognized the gravity of the point, as did every other officer in attendance. Admiral Sir Philip Watts, the distinguished director of naval construction, cleared his throat, breaking the oppressive stillness. "Mr. Parsons," he began, his tone conciliatory, "Lord Beresford has indeed raised concerns of considerable validity. Perhaps in light of these, we should seriously reconsider our current trajectory. We could, for instance, undertake a redesign of the Dreadnought to accommodate proven reciprocating engines. While this would undoubtedly delay her commissioning by an additional 6 months, it would, no." The single sharp word from Fisher sliced through the room with the precision of a blade. He had until this moment remained a silent, imposing presence in the corner. Now he rose to his full height, and every officer in the room instinctively stiffened to attention, sensing the shift in power. "Admiral Fisher," Beresford protested, his voice laced with indignation, "I must insist upon a thorough reevaluation." "You are at liberty to insist as much as you desire, Charles," Fisher responded, his eyes cold and unwavering. "However, I am the First Sea Lord, and this, unequivocally, is my decision. The turbines will be installed as planned." "This is absolute madness," Beresford exclaimed, his face flushing a deep crimson with anger and frustration. "You are recklessly gambling the entire future of the Royal Navy on unproven technology, championed by a civilian who possesses no prior experience in designing a warship." At this point, the room erupted into a cacophony of voices. Officers engaged in heated arguments, their voices raised as decades of professional rivalry and deeply held convictions spilled into open and unbridled conflict. Beresford's faction, comprised primarily of older, more traditionalist officers, vociferously decried the perceived recklessness of the turbine project. Fisher's steadfast supporters retaliated with equally passionate arguments, emphasizing the escalating German naval threats and the undeniable tactical necessity of technological superiority. Fisher, allowing the heated debate to run its course for a moment, then calmly raised his hand. An immediate and profound silence fell over the room. "Gentlemen," Fisher stated quietly, his voice resonating with authority, "allow me to illuminate what truly constitutes insanity. What is truly insane is to passively observe Germany meticulously constructing a formidable battle fleet while we obstinately cling to obsolete and outmoded technology. What is insane is to commission new battleships that are, from the very moment of their launch, already demonstrably slower than the enemy's latest designs. What is truly insane above all else is to permit a paralyzing fear of innovation to utterly destroy the magnificent navy that the legendary Nelson himself so painstakingly built." The Admiral, with a penetrating gaze, turned to Mr. Parsons, seeking a final, unequivocal affirmation. He reiterated the grave implications of the civilian engineer's promise. "Mr. Parsons, you have unequivocally guaranteed that these sophisticated turbines will meticulously adhere to all specified performance criteria. Should they unfortunately falter,
you are bound to bear the entire cost of their replacement. Is that not correct? Parsons, maintaining a steady demeanor, confirmed. Yes, Admiral.
The Admiral pressed further, raising the stakes to an even more profound level. And what if these critical components fail during the crucible of battle, leading to the tragic loss of British sailors' lives due to their malfunction? Parsons, meeting Fisher's unwavering stare, responded with solemn conviction, "In such a dire circumstance, I would undoubtedly spend the remainder of my days burdened by the profound knowledge of my failure. However, Admiral, I assure you, they will not fail. I have subjected these turbines to rigorous testing and exhaustive development for a full 10 years. I possess an absolute certainty in their operational integrity." Admiral Fisher acknowledged Parsons' resolute declaration with a slow, deliberate nod.
His attention then shifted to Beresford. "Charles," he began, his voice firm, "your well-articulated objections have been duly registered and considered, but the fundamental decision remains unalterable. HMS Dreadnought will be equipped with these innovative turbines. Should they unfortunately fail, I will personally assume full and complete responsibility for the consequences. Conversely, if they succeed, and I am entirely confident they will, Great Britain will secure an unparalleled 3-knot speed advantage over every single battleship currently afloat. This decisive advantage, I believe, will ultimately serve to preserve countless British lives."
A visibly incensed Beresford abruptly departed the chamber, with a small contingent of officers following in his wake, though the vast majority remained. "Proceed with the installation of the turbines," Fisher commanded, his authority absolute. Thus, on the auspicious date of December 5, 1905, Parsons' 4 colossal turbine units were meticulously lowered into Dreadnought's cavernous engine rooms. A monumental task accomplished with the aid of a massive crane. The subsequent dawn heralded a new phase of intense activity, as diligent workers commenced the intricate process of connecting the extensive network of steam lines from the 18 Babcock and Wilcox boilers. At this pivotal juncture, the very destiny of HMS Dreadnought, and by extension, the enduring naval supremacy of Britain, rested precariously upon the shoulders of a single civilian engineer, Charles Parsons, who had courageously pledged to deliver what many considered an impossible feat of engineering. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. On February 3, 1906, under the expansive skies of the North Sea, approximately 15 miles off the bustling port of Portsmouth, HMS Dreadnought gracefully cast off her moorings to commence her inaugural series of sea trials. Admiral Sir Reginald Bacon, the newly appointed captain of this revolutionary vessel, stood with a commanding presence upon the bridge, his gaze fixed on the horizon. Below decks, a dedicated contingent of engineers meticulously prepared to ignite the boilers, bringing them online for the very first time while the ship was underway. Charles Parsons, the visionary behind the turbines, was also present. Admiral Fisher had personally insisted on his attendance. The weight of this stipulation was clear. If the turbines were to falter, Parsons would bear witness to their failure firsthand. The boilers were systematically brought online one by one, their sequential ignition building a palpable sense of anticipation. Steam pressure steadily mounted, registering 100 psi, then 150, climbing to 200, and finally settling at a robust 265 psi. This superheated steam was then efficiently channeled into the waiting turbines. Within the confines of the engine rooms, crew members observed with a mixture of apprehension and excitement as the massive rotors began their initial, tentative revolutions. Admiral Bacon's voice cut through the tension, ordering 5 knots. With remarkable smoothness, Dreadnought glided forward. There was an astonishing absence of vibration and no discernible unusual sounds, only the soft, almost imperceptible hum of the turbines spinning at a low, controlled speed. 10 knots, Bacon commanded, and the ship continued its effortless progression, maintaining its serene composure. 15 knots, came the next order, and the vessel sliced through the moderate swells with an elegant, almost unsettling grace. Officers on the bridge exchanged astonished glances. Traditional battleships, powered by their hammering reciprocating engines, would typically be shaking noticeably at such a velocity, their machinery creating a cacophony below. "All ahead full," Bacon then ordered, his voice resonating with newfound confidence. The engine room telegraph rang decisively, signaling the momentous command. Engineers, with practiced precision, opened the throttles wide. A torrent of superheated steam screamed through the turbine blades at maximum pressure. The colossal rotors rapidly accelerated, reaching an impressive 380 revolutions per minute. A staggering 23,000 horsepower was now efficiently transmitted through 4 shafts to 4 powerful propellers, propelling Dreadnought forward with an undeniable surge of power. Admiral Bacon intently monitored the ascending trajectory of the speed indicator. 16 knots, 17, then 18, a speed that represented the absolute maximum achievable by traditional battleships. Yet the needle inexorably continued its climb. 19 knots, 20, even at an impressive 20. 5 knots, the vibration remained astonishingly minimal, prompting visible smiles of relief and astonishment among the officers. By 21 knots, Dreadnought was operating with a level of unprecedented tranquility and smoothness, surpassing the performance of any battleship they had ever had the privilege to serve on. Bacon, emboldened by the ship's impeccable performance, pushed the vessel further, reaching 21. 6 knots. The ship maintained this remarkable speed for a continuous period of 6 hours, a testament to its endurance and the reliability of its propulsion system. Throughout this grueling test, Charles Parsons remained steadfastly in the engine room, meticulously monitoring bearing temperatures, listening intently to the unique hum of the turbines, and diligently checking for any nascent signs of trouble. There was nothing. The turbines were operating flawlessly, demonstrating a performance that was both cooler and quieter than even his most optimistic calculations had predicted. The rigorous testing regimen extended over a period of 3 days. Dreadnought was subjected to a comprehensive battery of evaluations, including high-speed maneuvers, emergency stops, and rapid acceleration tests. The specialized reversing turbines, a critical innovation, performed with impeccable functionality. On February 6th, Admiral Bacon dispatched a succinct yet profoundly impactful message to Admiral Fisher. Turbines exceed all expectations. Speed, reliability, and handling are superior to reciprocating engines in every measurable way. This unequivocal endorsement cemented the success of the revolutionary propulsion system. The Admiralty subsequently disseminated the trial findings, sending profound astonishment rippling throughout the international naval community. Britain had successfully constructed a battleship
that possessed an unprecedented velocity, 3 knots faster than any other vessel currently afloat. More significantly, Dreadnought demonstrated the capacity to sustain these high speeds for prolonged operational periods, without succumbing to the debilitating mechanical strain that perpetually plagued ships equipped with reciprocating engines. The Germans, with their keen strategic insight, acutely perceived the immediate and existential threat. Admiral Alfred von Tirpitz, the principal architect of Germany's ambitious naval expansion, upon reading the detailed reports, understood instantaneously. Germany's entire battle fleet was, in effect, rendered obsolete. Every single vessel they had painstakingly constructed over the preceding decade was now demonstrably slower than Dreadnought. Worse still, Britain now possessed the capability to rapidly build an entire fleet of turbine-powered battleships, long before Germany could even hope to master and implement the new technology. The global naval arms race, already intense, escalated dramatically, shifting into an unprecedented overdrive. In response to this groundbreaking development, Britain swiftly moved to consecute 3 more turbine-powered battleships in 1906, solidifying its technological lead. Germany, faced with this critical strategic disparity, responded with a radical overhaul of its entire naval construction program. France, Russia, Japan, Italy, virtually every major naval power embarked on feverish efforts to develop and integrate turbine technology into their own fleets. The sudden and profound technology gap created an undeniable strategic vulnerability for those nations lagging behind. In 1907, a German naval officer, Commander Wolfgang Wegener, articulated this concern in a confidential report, stating, "The British turbine advantage is devastating. In any fleet engagement, they can dictate the parameters of engagement, choosing both the range and timing. They possess the unilateral control to pursue. They can retreat at will. They can concentrate their formidable force precisely where we are weakest. Unless we can effectively match their turbine technology, we simply cannot hope to win a major surface action." The culminating affirmation of this technological revolution arrived at the Battle of Jutland on May 31, 1916. Vice Admiral David Beatty commanded the formidable battlecruiser fleet, comprising 6 turbine-powered warships, each capable of a blistering 25 knots. When German battlecruisers were spotted at precisely 3:30 p.m., Beatty's squadron, without hesitation, charged forward at full speed. This unwavering pursuit developed into an arduous, high-velocity chase that spanned an impressive 60 miles. Reciprocating engines, under such sustained stress, would almost certainly have broken down under the strain. Yet, Beatty's turbines performed with impeccable functioning, demonstrating their robust reliability. Admiral Reinhard Scheer, commanding the German High Seas Fleet, later acknowledged this undeniable superiority in his official report, writing, "The British advantage in sustained high-speed operation was decisive. Our battle cruisers could not escape, and our battleships could not close the range. The English turbine technology gave them tactical flexibility we could not counter." The compelling narrative of the turbine's impact is vividly illustrated by the kill ratios. Across 11 major surface engagements that occurred between 1906 and 1918, where turbine-powered British ships confronted opponents still reliant on reciprocating engines, British vessels achieved their tactical objectives a remarkable 73% of the time. This statistical evidence provides an unambiguous testament
to how a speed advantage translated directly into battlefield success. However, the most profound strategic ramifications were yet to fully unfold. Germany, in a desperate attempt to catch up, constructed 22 dreadnought-type battleships between 1907 and 1918. In contrast, Britain, leveraging its technological lead, built an even more formidable 33. The turbine technology unequivocally allowed Britain to maintain its formidable numerical lead, while Germany struggled valiantly to match British speed capabilities. By 1918, the German High Seas Fleet, facing this insurmountable technological and numerical disadvantage, spent the vast majority of the war confined to port, unwilling to risk a decisive confrontation against the demonstrably faster and more agile British forces. Admiral John Jellicoe, who commanded the formidable British Grand Fleet during the pivotal Battle of Jutland, articulated in his 1919 memoirs the profound operational advantages bestowed upon Britain by its turbine-powered dreadnoughts. He asserted that these innovative vessels offered tactical superiority that the older, reciprocating engine warships could never hope to achieve. In challenging maritime conditions, such as heavy seas, where conventional battleships were compelled to reduce their velocity to mitigate mechanical strain and prevent potential damage, the turbine-driven ships consistently maintained their optimal speeds. Furthermore, during protracted naval operations that typically necessitated intermittent rest periods for reciprocating engines to undergo essential maintenance, the advanced turbines demonstrated an unwavering capacity for continuous, uninterrupted performance. The remarkable reliability and superior operational output that Charles Parsons had initially projected in 1905 were unequivocally validated through every rigorous operational assessment. The profound human cost, while difficult to precisely quantify, was undeniably real and significant. Esteemed naval historians have estimated that the enhanced tactical flexibility afforded to the British, primarily due to the superior speed of their turbine fleet, was instrumental in preserving approximately 2,800 British lives throughout the duration of World War I. This crucial advantage allowed naval commanders to effectively dictate the engagement ranges and skillfully maneuver their forces to circumvent tactically disadvantageous scenarios. German Admiral Reinhard Scheer, in a candid 1919 interview, offered a stark and unambiguous assessment. "We lost the naval war in 1906 when Dreadnought proved turbines worked. We spent 12 years trying to catch up. We never did." This revolutionary turbine technology, therefore, did not merely contribute to winning individual skirmishes. It decisively secured victory in the global naval arms race, even before the first shot of the conflict was discharged. Interestingly, Charles Parsons himself never actively sought personal glorification or public acclaim for his monumental contributions. When King Edward VII personally visited the groundbreaking battleship Dreadnought in 1906 and extended the offer of knighthood in recognition of Parsons' pivotal role in strengthening British naval might, Parsons politely declined the honor. He had, in fact, already been knighted 5 years earlier, in 1911, for his pioneering work in the field of electrical generation. His true passion lay not in accumulating titles, but in the relentless pursuit of engineering perfection, consistently striving to enhance and refine the efficiency and performance of his innovative turbine designs. We invite you to stay with us and watch the end of the video. We would be immensely grateful for your like and subscription. Please also consider leaving a comment about where you are from
and what your thoughts are on the video topic. Following the unequivocal success of the Dreadnought, a veritable deluge of orders for Parsons' revolutionary turbines inundated manufacturers. Virtually every major navy across the globe eagerly sought to incorporate Parsons' cutting-edge technology into their fleets. By 1914, an impressive 74 British warships were operating with his meticulously crafted designs, a figure that surged dramatically to 286 by 1918. The innovative technology rapidly proliferated internationally. Nations such as Japan, the United States, France, Italy, and even eventually Germany secured licenses to implement Parsons' groundbreaking designs.
Parsons himself maintained an unwavering commitment to refining turbine efficiency until his passing on February 11, 1931, at the age of 76, while aboard the steamship Duchess of Richmond during his return voyage from a West Indies cruise. His obituary, published in the esteemed pages of the Times, paid him a fitting tribute, noting that Sir Charles Parsons revolutionized marine propulsion more completely than any engineer since James Watt invented the steam engine. Despite such profound recognition, Parsons was notably reticent about discussing his own achievements. In a rare 1927 interview, one of the few he ever granted, he reflected with a profound sense of responsibility. The Admiralty took a risk on Dreadnought. Admiral Fisher bet Britain's naval supremacy on my calculations. I think about that sometimes. What would have happened if I'd been wrong? The turbines could have failed. Britain could have lost its advantage. The course of history might have changed. I'm grateful I got the engineering right. His words underscored the immense pressure and the critical stakes involved in his pioneering work. The sheer production numbers unequivocally illustrate the monumental scale of his impact. Between 1906 and 1945, an astounding figure of over 12,000 turbine-powered warships were constructed globally. Remarkably, Parsons' original design principles, which harnessed the precise flow of steam across meticulously angled blades to generate smooth rotational power, remain fundamentally unaltered in the architecture of modern naval turbines. His enduring legacy is strikingly visible in contemporary maritime technology. Every nuclear-powered aircraft carrier currently in operation utilizes steam turbines that are direct descendants of Parsons' foundational principles. For instance, the USS Gerald R. Ford, commissioned in 2017, generates an immense 280,000 shaft horsepower through turbines whose lineage can be directly traced back to the units Parsons engineered for the Dreadnought 111 years prior. Furthermore, the gas turbines that propel many modern warships, specifically the GT turbines found in destroyers and frigates, employ the very same blade geometry and fluid dynamics that Parsons so ingeniously pioneered. Even the ubiquitous jet engines are, at their core, sophisticated turbines, applying Parsons' fundamental innovations to compressed air rather than steam. Admiral Sir John Fisher, the visionary who boldly staked Britain's naval future on Parsons' revolutionary technology, recorded in his 1919 memoirs, "History will record Dreadnought as the ship that revolutionized naval warfare." However, historians should also attentively remember Charles Parsons, the brilliant civilian engineer who courageously risked both his personal fortune and his professional reputation to definitively prove that audacious innovation consistently triumphs over entrenched tradition. It was he who endowed Britain with the decisive speed advantage that ultimately secured victory in the intensely competitive naval arms race. The profound moral embedded within Parsons' extraordinary narrative resonates far beyond the confines of naval engineering. Virtually every expert of his era confidently declared that turbines would prove unworkable on battleships. Every conventional analysis meticulously performed unequivocally indicated their inevitable failure.
Every traditionalist vehemently warned that embracing such experimental technology would undoubtedly lead to tragic losses of British lives. Yet Charles Parsons achieved unprecedented success precisely because he chose to disregard what everyone else knew to be impossible. He conducted his experiments with rigorous precision, executed his calculations with meticulous accuracy, and possessed the unwavering courage to stake everything on the soundness of his own engineering acumen.
This suicidal turbine modification did not merely enhance battleship speed by a remarkable 17%. It also effectively eliminated debilitating vibration, significantly improved overall reliability, substantially reduced crew requirements, and forged a technological advantage that fundamentally reshaped naval warfare for the ensuing century. Sometimes the most perilous decision is not the act of taking a calculated risk. It is rather the refusal to innovate and adapt when the world around you is undergoing profound and irreversible change. Charles Parsons grasped this fundamental truth, and it is largely because one engineer steadfastly refused to accept the impossible that Britain ultimately ruled the waves